finished the lecture material, do the course evaluation, and Caleb is coming for the last demo. Yay. And you need to pick up your midterms. If you ask me to remark anything, it's in these folders here. So you need to pick up your midterms as well. So before I go to the lecture material, this is the last slide that we left off with, I want to remind you that we're having a final exam in this course. I hope that's not a surprise. So the final exam will be a week from tomorrow, 9 o'clock in the morning in the McKinnon gym. And if you've never written an exam in the gym before that exam, I suggest you go over and just look at the sea of desks so you're not intimidated by it when you get there. So you need to bring your student ID card. You need to sit in an assigned seat. There will be a piece of paper. This is kind of important information. So even if you plan to miss the final exam, you might be quiet so others can hear it. So you need to sit at the desk that has your name on it. And if there are 12 Coddings in this class, I have to sit at the desk that has Penny Codding on it. Okay, so you have to find your name. And you will be sitting alphabetically, so you won't be able to sit with your friends. You have to leave everything at the front or the back of the gym. There will be almost 900 people there. So very flexible, easy to melt. If you've ever brought your groceries home and put them on the stove and discovered that the stove was on, you know this. And you can tell that I'm a danger in the kitchen. So that's one thing. But if we could make the chains longer, and this was actually the subject of a Nobel Prize. Two men whose names are Ziegler and Natta invented a catalyst that would cause the polyethylene reaction to run much more smoothly and at lower energy, and so they could make really long chains. So we'd have, say, 10,000 monomers in the chain rather than 500 monomers in the chain, and get these large molar masses. So we end up with high-density polyethylene, and now we can make things like those hard black plastic pipes. If you walk around in the stairwells of the Elliott Building now, you see these bizarre, huge black pipes running down the stairwell. Right? One of them is labeled as an emergency exit. But that hard plastic pipe is actually this high-density polyethylene. So we can make these kinds of changes. And here's an example of the physical properties and how they change with the amount of crystallinity. So we're just talking about making little areas of order inside a mass of cooked spaghetti, if you will. And as we increase the crystallinity, look at how the melting point goes up and how the density goes up. Now the density is not changing by a dramatic amount, but then the stiffness of the material goes from whatever this number is, 25, to 165. So we can increase the stiffness by a huge factor just by increasing the amount of intermolecular interaction between the chains by how we manufacture the polymer. So that's an important part of polymer chemistry, is how we can control the structures of the materials by, I guess I don't have low density there, by changing their physical properties in simple kinds of ways. Now another way that we can change polymer properties is to fool around with the length. I just talked about that here, the strength of the chains and the stiffness of the strands. So those are things that determine polymer properties. Also the shape of the chemical backbone and what kinds of groups we attach. And we've already talked a little bit about the groups. Because remember I said if we had ethylene, then we can do that addition. If we do that addition reaction using polyethylene. But if we took that ethylene and put a chlorine in place of one of the hydrogens, then when we made the polymer, we had polyvinyl chloride, which has quite different properties. And if we replace that chlorine with a benzene ring and made a polymer, we now are making styrofoam or polycarbonates, depending on how we manufacture the polymer. So styrofoam is manufactured by adding something that bubbles into the mixture, the liquid mixture of polymer. And so as you try to manufacture things, the bubbles create those little circles and spheres that you see in the styrofoam cup, and you press that into a mold. But you can make polycarbonates. In fact, some of our clear plastics not the flexible ones like the pop bottles that I see in front of me, but a hard one, perhaps like your drink bottle there, are polycarbonates where they manufactured, it's the same thing, it's just polyethylene with a phenol ring on it, but they manufactured it without a bubbling agent, pushed it into a mold, and now it makes a hard, clear plastic. So we want to understand a little bit about how we can manipulate the properties. We're touching on a subject that is huge, and we're just doing a little bit of a brief review of it. This is the water, but what we really want to understand is what is going on inside there with respect to the molecules. What are those properties there? So the molecular properties, they tend to be organic molecules. They tend to be much longer than they are wide. So you see these long, skinny guys, and here's an example of it in a space-filling model. And they also are stiff and rod-like. So how would we get a stiff molecule? Well, one of the ways to do that would be to add some benzene rings. So you'd have these flat areas, right, with their high delocalized bonding top and bottom. That would give you this inability to make a wiggly kind of chain. And also double bonds would give you some stiffness as well. So notice we've got this acid group here. They also tend to contain polar groups. So you see a lot of that here. We have polar groups and we have nitrogen. That nitrogen would have some non-bonded electrons. We've got some polar groups here. We've got some stiffness there. This was liquid crystals were first discovered by somebody who was studying cholesterol, and there is a particular kind of structure that's called the cholesteric structure, and this is actually the kind of liquid crystal I had in this thermometer that I stuck on my baby's head, because it was sensitive to changes in temperature, and the various layers would align differently as it warmed up, and what a light passing through then would be twisted and show different colors. So the cholesteric structure, you have top and bottom structures that are lined up and intermediate structures that are twisted at an angle. So as light travels through here, the light gets turned as it goes through this structure. And that gives you these color patterns.